So welcome everybody to, this is the AI theme of this first online CICSA conference. And as you know, the theme of the conference is all about sustainability. So I'm Emma Hart. I co-lead the AI theme for CICSA with my colleague, Professor Helen Hasty, that you should also see there on the video. So welcome to the AI theme. So we have three very exciting talks for you today, all on the theme of sustainability. So we have a couple of talks that are really looking at how we apply AI to applications in order to achieve some sustainable goal. And our final talk is more concerned with the development of new AI, and that's particularly looking at something that's actually very important in when we are thinking about applying AI, and that's about fairness when we develop algorithms. So we have a talk about using AI in renovating existing buildings, followed up by a talk about designing new buildings and the role for AI in achieving sustainable goals, and finally a talk about energy management and achieving fairness. So I hope you enjoy. Just to say, if you have questions, if you can type them into the platform as the talks are going along. We're going to take all questions at the end after the three talks. So if you can just type your questions into the platform, if they're directed at a particular person, maybe if you could put the speaker's name in the comments so that we can see who the question's directed at. So I'm going to hand over to Helen now to introduce the first of our speakers. Thanks.
Great, thanks, Fred. Thanks, Emma. Fred, if you could just share your screen, that'd be great. So it's my pleasure to introduce Dr. Frédéric Bochet. He is a senior lecturer in construction informatics at the School of Engineering at the University of Edinburgh, where he leads the CyberBuild Lab. He's also a member of the Centre of Future Infrastructure and a fellow member of the Edinburgh Centre for Robotics. He's published over 70 publications and is currently the president of the International Association for Automation and Robotics in Construction, amongst other posts and accolades. So without further ado, I'll hand over to Fred, who will give the first talk. Thanks, Fred.
Okay, thank you very much. That was an overly kind introduction. I hope you can all see the screen and maybe myself as well, because I can only see the screen I share at the moment, at least. The talk I will give you today is about a EU project that is ongoing. It's called Beamer. It will be about, there will be some aspect of AI, but actually it's a lot about an overall integration, an ICT integration, and this includes some AI components, and I will highlight these. I will also, in one area that we work in, I will also highlight some area where we haven't used AI, but actually this is an area where some people are starting to investigate the use of AI to support those works. So there you go. Just to give you an idea, it's a 3.5 year project that includes 15 members. And Beamer, what does that mean? It means beam-based holistic tools for energy-driven renovation of existing residences. Most of the title makes sense to you, but you may not know what BIM means, because this is very much a construction industry terminology. BIM means building information modeling. And what this is essentially, you can think of this as the digitization of the construction sector. So construction historically is not digital at all. It's all paper-based or using traditional other tools and lots of hand activities. But there has been quite some efforts over the particularly last 2 decades to start digitizing the industry. And it's work in progress. There's now quite a lot of consensus behind this, and there's a lot of progress happening, but there's still a lot of work going on, and hence there are many research projects that are still being funded on the use of BIM and other technologies, digital technologies, to support the industry. Well, I'll go quickly on this, but the objectives of the projects, especially the two first ones I will highlight, is to develop some new tools and techniques, mostly ICT-based systems that support both the design and the construction aspect of the renovation project. And an important aspect of this is the establishment of semantic interoperability. So when you think about construction projects and renovation project, that actually involves a lot of disciplines. And so, there's a lot of data sharing that needs to be done, and actually data aggregation in order to support tools like AI. And for this, you need to really enable this smoothless exchange of data. And for this, you need to create semantic mappings between different data models or ontologies that exist among different domains. And this is actually, it's not the only thing we do. In fact, our lab is not involved in that aspect very much, but actually I think it's an important work of the project that I will touch on briefly in one slide. Just to give you an overall idea of what is Beamer and what is what we call the Renovation 4.0 package. If you look at this slide, on the left-hand side, we have the development of tools about the acquisition of data, so getting data input into the process. Then we have in the middle what we call the Beamer interoperability framework, which is essentially about collecting all that information, but also enabling those semantic connections between the different data. We also have input of a lot of legacy information. So if you want to do the renovation of a house, especially from an energy viewpoint, you will be interested in doing energy simulations. And to do this, you will need, for example, weather data. And so weather data can be collected by our system and linked to the projects in order to support simulations and in some cases, application of AI. And finally, once you have all this, you can use all that information to do some simulations and that support decisions. So we have an entire decision support system that use a lot of subtools to support that. And finally, there is an area of work in the program of Beamer, which is about the actual delivery of the project. So supporting the workflow of the construction crews that work on site to enable them to efficiently and effectively conduct the renovation that has been designed. So I'll have a look now at some of the, a few of the tools, because we develop a number of tools in that project, but I will look at, I can't remember, 3 or 4 tools that I thought are relevant, especially because some of them are employing some AI. The first tool, the 2 tools I'll look at are scan-to-BIM tools, and this is actually the work that the University of Edinburgh has the charge of. What is scan-to-BIM? The idea is that we can go inside buildings, record a lot of 2D and 3D data, so point clouds and images, and from this, we need to create a 3D model of the facility, because that model is then used to do energy simulations, to plan the renovations, etc., etc. So we need to create that 3D model. And at the moment, this kind of process is done manually, but we've been looking at developing techniques. We're not the only people doing this, but there's a lot of effort at the moment, certainly this. So here's just an illustration of where we are at. I should highlight we are a third of the way through the project, so it's not like we've completed. Many of us are still progressing some of this, but you can see in this video, we showed first the point cloud. I shall go back a little bit. That's the point cloud. Then we detect the walls inside the building and the openings as well, actually, at some point. We then create a 3D model, which is semantically rich. That is, in the model, we just don't create geometry, like a mesh, for example, but we actually create semantic objects. So we create walls in that case and openings inside the walls. We also create floors, ceilings, and actually from that information, we define other properties and other objects that are of value for energy simulation. In particular, if you look at these boxes, these would be called second level space boundary representations. And this information is important to support energy simulations and energy analysis. So we extract this all automatically from the point cloud, generate the model, and this is passed on to the other tools that deal with the energy simulation and the design of the renovations to be applied. We haven't done everything. There are some bits I'm still working on. One of the things we haven't done in that particular area is actually apply AI. We apply mostly traditional computer vision techniques, but there's certainly room for AI, and there are people that have been started looking at applying AI in that domain. So trying to do essentially semantic segmentation of point clouds to identify which point is a wall, which point is a ceiling, which one is floor, etc. An issue with this is getting data sets. That actually yesterday I was talking to a company that seems to have a lot of data for that. So that would be interesting to investigate. So no AI here, but certainly a lot of space for it. The second component of the scan-to-BIM is to enrich the 3D model we just created with additional information of the building. In particular, we're interested in detecting what we call MEP components. So MEP goes for mechanical, electrical, and plumbing. Because this is important, again, to support the renovation design, and importantly also for the construction effort that needs to be done. So if you need to change the materials in a wall, you need to know if there are electrical components in that wall, because that will have an impact on cost and many other things. So in this, we've done some work. We're quite early in that particular package, but the first thing we've done is develop a RCNN network to detect radiators, sockets, and switches inside images. And we take a lot of images of the interior of the buildings. With these images, we do some 3D reconstruction using structure for motion traditional approaches. And then we want to align this with the laser scans so that we can reproject the detections we have onto the 3D model of the structure and add the components, semantic components of these electrical components. So this is work in progress. The results we have on using RCNN are quite good. One interesting thing we did here is we initially worked with 360 images that we acquired inside the building. And then the problem with 360 images we had was creating 3D reconstructions that were working well. And so then we also had some work with traditional pictures, like camera images. And then one of the things we were interested in is, like, actually, if you train a deep learning network on 360 images, how is the learning transferable to standard images? And it turns out that actually 360 images are actually quite good for learning detectors. And we were able to apply the model to standard images quite well with success. But the other way was not working so well. So it would appear that the different level of distortions that you get into 360 images were really good to provide variety in the appearances of those objects, and therefore the models were much better transferable. Okay, so this is the, sorry, I should finish. This is the scan-to-BIM. Another tool that some colleagues are developing, so this is not us, these are our colleagues in Greece. It's a tool called Aripva. Don't ask me what it means, because every time I try to remember, I make a mistake. But essentially, the tool is about doing AR-based in-situ 3D model review. So once the scan-to-BIM has happened, what we would anticipate is that for various purposes, but one of the purposes would be verifying the model, for example, is going on site with the goggles and walk around the building and see essentially the 3D reconstruction overlaid, and enabling the person to possibly add things that were missed, or correct certain aspects, or later on to actually monitor construction and support construction works, for example, to show to workers what needs to be done where. Some of the key components here are indoor localization and object detection, which I will look at. To do this, essentially, they need to align the 3D model that was reconstructed with the real environment. So as we know, AR goggles like HoloLens can reconstruct the 3D world they are in very well. But then we need to align the 3D model of our scan-to-BIM reconstruction so that they can see it overlaid on their view. And to do this, they've had to work with different tools, especially to transfer the semantically rich models and all the semantic information into a format that they can use, that they use in Unity to support the AR application. So they have here just a quick example. The way they do the alignment right now is using a tag, a marker here in the rooms. Obviously, this is not ideal, and you wouldn't want this used in practice. But they would probably use some component like doors or windows, something that are quite easily detected and used as a natural marker. And I stopped the video here because you can see there's a door frame that is starting to appear, and that door frame is an object from the scan to BIM reconstruction, okay? And there was another closed door that we saw earlier. So people can see how things are looking in the reconstructed model compared to reality. And you could also show what renovation needs to be done where. Then another thing they do is they've been working on themselves is to develop a similar object detection model that we did. This is because if our socket or switch or radiator detector fails to detect something, they would need to add it themselves. And so they've been looking at using a very different deep learning model, like a tiny YOLO V2, because they need to have a lot of speed in their case. And they were testing it using a similar data set. And well, as you would expect, it doesn't work quite as well, but they had some reasonable results. And one of the good things is once you're on site, you can really have really good view of the components to guarantee that they are well detected. Now, the next step that I mentioned earlier is to do the energy analysis and define a suitable renovation strategy from an energy viewpoint. And for this, there is a tool that is called Reno DSS, which is for Renovation Decision Support System. And that has a number of subcomponents, but I'll have a look at a couple of them that are quite interesting. They have a component of building component database design and development, which is essentially developing a database of commercial components that exist out there that can be used for the renovation. So not just put standard renovation materials, but actually existing one from the market. They have the renovation lifecycle analysis and lifecycle costing, which is important from a sustainability viewpoint. They have a building energy performance modeling tool. And actually, the energy analysis is not just done at the building level, but actually takes into account energy, energy generation and usage within the neighborhood. So the idea is to have the current neighborhood energy usage and energy renovation drive the solution, or at least be taken into account when designing the current solution. Actually, I'll skip this one, but I'll move to the LCA and LCC model. For this, essentially, you would need to have the semantic 3D model of the facility, which is what we provide through the scan to BIM. You need to have a lot of information about the materials that make up that building. So the existing materials, but also the materials that you are designing to put in. And now with new databases that we are developing, we are able to have a lot of information attached to material. So not just how much they cost to buy, but actually maybe maintenance cost, end of life cost, the payback period for some of these materials, especially from if you're looking at solar panels and other energy generation solutions. This is important. And then there are also sustainability KPIs that we need to know what is the embedded carbon and what is the impact on nature for the production and the operation of those materials. So this all information is all taken into account in order to conduct some life cycle analysis and life cycle costing in that module. Now the search for the right design or the right renovation strategy is driven by simulation. And for this, they take again the 3D model that is generated of the facility, and they must analyze it. But to do the analysis, they need to know how the space is generally used, okay? And for this, you need to have occupant behavior models. So that's the box 2 on the right here. And how do you know how people behave in different buildings, especially the building you want to renovate? So for this, what we do is we are equipping some validation sites with sensors about humidity, temperature, occupancy of the rooms, and CO2 rates inside the air, and other sensors. We look at energy usage, and essentially we are trying to, one of the things we're trying to do is create some different occupant behavior models, okay, to understand how people use the space. Do they leave the heating on and then open the window very often, and things like this, trying to understand how people use the space, because if you don't do that, the renovation strategies you'll put in place, they'll just not work. And this is a problem that has occurred a lot already. And for this, so we've been collecting all that data from current occupants, and we are still installing more sensors right now and collecting more data. And my colleagues who are dealing with this, they are trying to apply machine learning techniques to essentially create models that are representative of how people behave. So at the bottom here, I show that they've been using like Gaussian processes, for example, and multivariate Gaussian Bayesian classifiers to fit essentially models to different occupant types. Sorry. So the last thing I wanted to talk about very briefly is about the new ontology, because we don't make use a lot of AI in that project yet, but there's certainly a lot of opportunity for it. And as I mentioned earlier, the opportunity arises when you can link various data sets together. And for this, you need to create data models that are able to encompass all different data sets. And some of these data sets come in open formats and open standards. And so you need to create mappings and connectivities, and sometimes even enhance existing ontologies to do that. So you can see here in the 2 boxes, we are looking at 7 domains right now, and we have completed, well, we have integrated certainly 4 domains, occupancy profile, sensor data, KPIs, weather. In fact, since that slide was created, we've made much more progress. We have also integrated some building domain data and material properties. The renovation measures are still being happening. So this will open some opportunities certainly to data analysis. I'm almost finished, Helen. So just to say one last thing, we just don't work with existing data set. We actually have some validation sites, and we have 4 different housing cases in 4 different countries. So they have different weather, they have different pattern usage, they have different context. So it's quite interesting to work with that. And it does create challenges in terms of acquiring data. For example, right now I'm facing issues about taking pictures of flats where there are residents. People don't like their flats, pictures of their flats being taken. And it's something we have to negotiate or work with. And I think this raises some interesting questions from some ethics and maybe like more general GDPR matters. Well, I was going to say one last thing about challenges and lessons learned, which is nothing to do with AI, but about the project. You know, I wish we could just do AI and computer vision and all these things every day, but most of the project is nothing about that. It's like we're spending our time in meetings, and I think there's a lot to be learned about death by inadequate meetings. And so you need to budget your management time quite well in those projects. There's the project external reviewer, so that's quite interesting. We have an external that is quite aggressive, might be a bit hard word or harsh word, but he's very involved and very keen to have an input. And so you need to manage that. And that includes some of the decisions even related, you know, picky decisions about which algorithms to use here and there. And I think that has been quite interesting. And you need to be quite diplomatic around this. And finally, COVID has been quite an impact on that project. Not so much as other projects that have to do lab work, etc., but certainly we've had to revisit some way how we interact, and we actually lost 2 industrial partners due to bankruptcy, that project. And in those new projects, for people who have never experienced this, you're still bound to deliver. If you lose partners, that's your problem, and you have to deal with that. And it all goes back again to spending a lot of time doing management. And I think it's something for young people who haven't worked in these areas, something to know that you spend, you know, it's an important aspect of delivering projects like this. Thank you.
Okay, so thank you very much, Fred. So I'm going to introduce Francesco now, our next speaker. So Dr. Francesco Pomponi is Associate Professor of Sustainability Research at Edinburgh Napier University, and also academic tutor at the University of Cambridge's Institute for Sustainability Leadership. So he's an industrial engineer by training. He worked 6 years in the construction industry in Italy and the UAE before coming back to academia, where his research focuses on the practical challenges of enhancing sustainability in buildings and in construction. So with that, I'll hand over to Francesco. Thank you.
Thank you, Emma. Apologies for the fake background, but I'm in a corner in my bedroom, so it's probably nicer. Hope you can all see my screen. I want to talk today about a couple of things, really. One is some work that we did. It's been a collaborative project, but also what I think, due to my background, are potential future applications for AI to address sustainability. So since we can't meet in person, I thought I would clarify a few things just before we get started. I'm Italian. If my accent doesn't give it away, my nose does, and I'm bald. So that's me. But what I'm not that handsome guy. I haven't got a head full of hair. And most importantly for this talk, I'm not a computer scientist. You know, Fred's presentation was full of cool stuff, and I just want to make sure your expectations are adjusted to an engineering background. So the first project I'm keen to share with you is this project called BEETLE. I love good acronyms. And BEETLE stands for Built Environment Efficiency Tool for Low Environmental Externalities. I like Fred's work. We're also interested in lowering the environmental impacts of buildings and construction. That's because their share is huge. Before I describe a bit further this project, I need to introduce a key concept, and that's embodied carbon. Now, whichever building you're in today is probably a building that you conceived as a finished product that meets your needs. And that's the purpose of buildings, you know. They provide shelter, they make us comfortable, we live in there, we have fun in there, we work in there. But there's a lot that happens before and after the useful life of a building. So we refer to the useful life as the operational stage, but then there's extracting natural resources, turning them into useful products and assemblies and components, shipping them to site, having huge cranes. For those of you in Edinburgh, you'll know the new centre, John Lewis Centre. It's been there for, I don't know, 4 or 5 years. Huge environmental impact of construction. And once the life of a building is ended, we need to do something with it. So there's demolition, the construction, a lot of stuff goes to landfill. All of this, everything which is not blue in the slide, it's called embodied impacts. It's a misleading name because the emissions and the carbon are all but embodied, that they're long gone into the atmosphere. But that's how it is. It's name defined in the 1980s. I wasn't born, so I couldn't do much about it. Now, if you think of building structures, and I put there the 3 main structural topologies that we use nowadays, pretty much everywhere in the world. That's reinforced concrete, steel, and lately, also mass timber buildings. So if you think of a building structure, there isn't much that you do to it during the operational life. In some cases, yes, there are major refurbishments, or if there is in a seismic zone and an earthquake that damages it, but these are kind of exceptional events. Otherwise, the life of a building goes without bothering too much the structure itself. We take non-structural walls down, we patch them up, we change a few things, we paint, but the structure stays there, nearly untouched. So in the case of a structure, you can easily understand that the environmental impacts are all linked to the embodied carbon, which therefore becomes a huge and very, very important consideration for the structural design of buildings. So I won some funding from the EPSRC, and this is the project without computer scientists. So we spent a couple of years perhaps working on this, and we produced a tool. It's for Rhinoceros, which is a 3D design software quite used in the construction industry and also for parametric design. So the way it works is fairly simple in a way. So we have a user interface. It requires inputs by the users. You click compute, takes some time, and then it produces a realistic design of the structural frame of a building and gives you this probability density function of its embodied carbon. The probability density function is linked to the uncertainty that we have. For instance, if we're talking about a steel structure, we don't always source the steel from the same supplier. Can come through a different supply chain from different parts of the world via different means of transportation. And therefore, there is an inherent variability to the value that we have for the embodied carbon. Now, this figure over here is the one we put in the published paper. And of course, we wanted to look really good. So we tried a simple structure, we click compute, and we did get a result in 7 seconds. And we were quite pleased. However, when you start trying to analyze more complex structures, since this algorithm works on solving differential equations and uses a method called finite element analysis, it has to go through a huge catalog of structural steel sections that are available, and it works out the optimization of the 3D frame. So it takes a while. And after 2 years, we were limited in terms of time because complex structures would take quite a significant time, and we could only address steel structures because of the complexity of the mathematical modeling behind the tool and the fact that we had to solve those equations each time. So I went to Emma, Professor Emma Hart, and I thought that we could collaborate, and this is what we achieved with computer scientists. Now, I just want to make sure it doesn't sound as if I'm saying engineering is crap and computer science is solving the world. I think I want to highlight the potential for collaboration. What we achieved by working together is having something that works for the 3 structural typologies that I've showed you before, and they are pretty much the only structural typologies that are used nowadays. So it kind of covers everything. And we have something that, as you can see from the animation here, works pretty much in real time. So that's the beauty of AI, where I feel the interdisciplinarity and the collaboration was great is in the fact that we felt very useful because we provided the 20,000 structures that enable to have a sufficiently large data set, which has then been split into training and testing and allowed us to achieve this. There's 2 versions of this tool. One is for SketchUp. It's a software tool originally developed by Google, now owned by Trimble, and is widely used by architects and designers. And then there's the second one, the one that's moving in the slide, which is a standalone version for engineers who generally don't tend to use SketchUp. And that was the first bit. So a couple of years of work, and we achieved something which was limited and time consuming, computationally expensive, and then collaboration with computer scientists, introduction of AI, something that is streamlined, works in real time, and enabled better way of supporting environmentally conscious decisions. This is another example of a work that we recently did. And it all started when Microsoft released the footprints of the 125 million buildings in the United States. So those are 2D footprints. So you just see the perimeter of the building. And then there is a subset of those 125 million buildings, which has a 3D piece of information. So you also know the building height. And already this data set, of course, relies heavily on AI, but we just got it from GitHub. And the reason why we were interested in working with this data set is because there's a number which is very simple in its definition, but has profound impacts in its use. And that's the floor area elasticity. It simply says how much space each of us has in a nation. And there's generally two ways of estimating it. One is top-down and the other one is bottom-up. So the top-down approach, I'm giving two examples, both related to the United States, is working out total area that you have, dividing it by the population and trying to figure out a range. The fact that you see a range, the 3,111 square meter per capita, is due to the fact that the social status has an influence in how much space you own or are responsible for, as well as where you live. So if you live in a densely urbanized downtown versus the suburbs, that's why we have some variability there. A bottom-up approach instead starts from the survey of individual buildings, and then you aggregate that across the whole population in order to work out the floor area and try to work out again a range. You can see that two ranges are, within the same order of magnitude, but fairly different in a way. There's also additional issues, like one of the most widely used number about floor area elasticities in the world is produced by the International Energy Agency. And it's really not that transparent. When we asked, how did you estimate this number? We couldn't get an answer. There's generally no uncertainty. You just have a range. You don't know how the numbers are distributed within that range. And in the case of the bottom up, it's very limited. For instance, the EIA surveyed only 5,600 buildings in order to tell us something about the 128 million. So the sample population is truly, truly small. So we thought, can we have an AI-based approach to address this? And I beg you to consider that this is a manuscript under review. I was very keen to show it to you today, but please don't share it. We wanted to understand from the Microsoft dataset how different this full-scale estimate of floor area elasticity would be compared to the numbers already out there. So someone had already tested the dataset for accuracy, and we knew it was accurate, but we also knew there were false positives, lakes and forests and stuff like that. It took us a while to figure out how to identify this and to classify them. And eventually we reflected that if it is a building, it has to be within a reasonable distance of a road. You need to be able to access it somehow. So we tried different steps and realized that when we hit the sort of 300-meter distance between the center of the building and the road, we are covering about 90% of the area. So that seemed a reasonable threshold in order to distinguish between buildings and false positives in the data set. Another thing that we had to do is infer information about the building height from the building footprint. Because remember, 125 million buildings, you only have the footprint, and for a subset, which is 8 million strong, you also have the height. So there's a lot I've learned that you can derive from a building perimeter, and we tried 19 different metrics ranging from simple one to the complex ones. And we tried a bunch of different regression models. Remember the first slide, I'm not a computer scientist, so one of my PhD students did this, and we used a 70-30 training to test split, and ended up using the random forest regression model for our work. You might think, so what? And I'll try to guide you through this slide because I think the implications are quite significant. So these guys, some academic groups really established in this field, as well as government bodies, have produced the numbers that we are using for policy and decision making. And the numbers are here. So these are the dashed lines. You can see that they vary a little bit, but are pretty much around the 100 square meter per capita. And we're talking about North America, so United States and Canada in this case. Now, we did a sort of a reverse engineering approach. So we grabbed our data set and said, okay, let's assume different percentages of the building stock that are multi-story. And let's see what is the percentage that we need to have in order to meet their number. And basically, in order to have the same result that these guys had, we need to assume that no buildings are multi-story in the North American building stock, so in the US and Canada. And you can instantly see how absurd it is. Even if you've never been in the United States, you must have seen movies and stuff like that. So you know that the vast majority of buildings is indeed multi-story. And as we increase this percentage, we get further away from the numbers that have been used so far in policy and decision making. I don't want to say that 100% of the building stock is multi-story, but surely I think that the reality is somewhere between these two. So the reality seems to be nearly 3 times as much as what's been used so far. And the implications of this are quite significant because of where these numbers have been used. So they've been used to forecast the heating and cooling energy demand in 2100, sorry. And with a different area, actually, the forecast heating and cooling energy is much, much higher. These numbers have also been used to project the floor area space due to a growing urbanization in the global south. And if the floor area elasticities are wrong, then the projected space is equally wrong and is much higher. Same stuff for the material stocks in North America. So what is that will be available in 2050 or that will be embedded in North American buildings? And again, the quantities of concrete, steel, aluminium, glass, wood, whatever, are much higher. This also implies that we will be using more resources than we currently think in order to build that building stock. The only positive news is that if buildings are larger in floor space than we foresee, then by switching to a mass timber building, the possibility of storing carbon is actually greater. And that's the only positive news of having severely underestimated the floor area elasticities. Now, these 2 projects are the thing that we wanted to present today, but it's also a bunch of other questions that I've had in mind for a while. And I kind of thinking that the only way of meaningfully addressing them is through a collaboration between sort of engineering and computer science fields. And even if we can't touch each other, I think there's ample scope for collaboration. Some of the questions there, we do know what is mathematically speaking the optimal shape of building, but it's a simplified mathematical proof that doesn't take into account of all the things that you've seen in Fred's presentation, for instance, about the user's behavior, the orientation, the different variables that play a role in the operational energy of a building. So it's almost impossible without AI to answer that question. Google has released a wonderful data set on our personal mobility. And we know we spend less time in offices and more time at home. So can we use that to predict the energy? And then can we learn from that in order to forecast how mobility influences energy consumption in buildings? And therefore we can optimize, for instance, the use of renewable energy in the grid, because we know exactly when peaks will occur. How many buildings do we have on the planet? I'm really curious about that, and we don't know. How many get demolished and built? Can we use satellite data in order to understand that and be accurate? We're really rough on the estimates at the moment. It's really coarse, the sort of information that we have. And then to conclude, this is something that it's not perhaps too dissimilar from what Fred was talking about, but slightly different in the sense that it really boils down to societal engagement and participation. And I've had this in my head for a long time. I'm thinking that we do have the technology in order to engage with building users. So we could all log information on the buildings that we own or live in or know of. AI could understand the materials, and we could have digital twins of each building. We could know exactly the materials that are embedded in each building. We could know that where the building is in its service life, when it's likely to be demolished or when it's likely to be refurbished. We could understand buildings that are going down and going up. And therefore, we could truly enable a circular economy that links material exiting a building to the material entering a new building. And I would be truly keen to collaborate with anyone who has an interest in progressing in some way towards this. That's all I have. Thank you very much.
Great. Thank you very much for that interesting talk, Francesco. We're going to save questions till the end, but it'd be really good if we could have some questions. So please go onto the platform and post some questions under the artificial intelligence theme. And next we're going to move on to Simon Powers. So if you'd like to share your screen, Simon.
Yeah.
Great. So Dr. Simon Powers is a lecturer in the School of Computing at Edinburgh Napier University, where his current work looks at agent-based computing to help households and community energy systems to self-organize to reduce their electricity consumption. He is the associate editor for the IEEE Technology and Society magazine and an associate editor for adaptive behavior. He has also held a fellowship at the Kiel University Institute of Liberal Arts and Sciences. It's very interesting. And so I'll hand over to Simon.
Great, thanks, Helen. Okay, so generally my research is in using artificial intelligence to help communities, groups of people solve social problems. So I have a background in the human sciences, a bit of a background in social sciences, game theory, economic modelling, that kind of thing. So I was kind of, early on in my career, I was used to looking at issues like climate change and other social dilemmas from the perspective of economics, game theory, human social sciences. What I've become interested since is how can we use computing technology and artificial intelligence in particular to help communities and groups more easily be able to solve these problems. And the big one that I'm interested in is climate change. So what I'm going to introduce in this talk is how artificial intelligence can help a community to regulate its energy usage. So this is a really important thing for us. So the UK government, for example, has legally committed to reduce greenhouse gases by 80% by 2050. And the only way that we can possibly do that is by shifting to renewable energy sources, so solar panels, wind turbines, that kind of thing. And in principle, that's really good. So there's no reason why we shouldn't do that. That's a good thing to do. And indeed, it also seems good from an economic point of view. So for example, it's stimulating job creation in these areas. So shifting to renewable resources is a good thing. But the problem is with the way that electricity is distributed at the moment through the centralized national grid, it's actually very difficult to integrate renewable energy sources like wind turbines and solar panels into that. So the national grid essentially is set up from a supply side management point of view, whereby if the amount of energy that a town or a community is demanding at one point in time is going up, then the national grid will just meet that at the supply side by generating more energy for them. And they can do this because, for example, if you've got a coal-fired power station, it's relatively quick for you to fire that up and to produce more output from it if needed. So the national grid at the moment can relatively easily turn on and off its coal-fired power stations to meet demand and meet its predictions of demand. With renewable sources, that's not really possible, or possible much less, because of the fact that they are dependent on weather conditions. So if you're in a tropical country, this would be fine, where it's guaranteed that weather conditions are roughly going to be the same for the whole year. But of course, in Scotland, that's not the case. We know how variable our climate is. And this means that we can't just turn on and off solar panels, turn on and off wind turbines to match demand. What we instead need to do is think about how can we regulate demand so that it's not exceeding the amount that we can generate from our renewable sources at one point in time. And it's easiest to do this, and it's easiest to integrate renewable energy sources into an electricity grid if you do that on a local scale instead of trying to do it centrally at a countrywide scale. So the idea is shifting energy generation down to the local scale, something known as microgrids, which is what you can see in the lower left image down there. So the idea is a local area, a local community, which might, for example, be a town with some businesses, some residential areas. They will have their own solar panels and their own wind turbines, and then they're going to use as much energy as they can from that themselves. And this is definitely a strategy that the Scottish government and the UK governments are pushing. So they're pushing the idea of community energy systems where renewable energy sources are owned by a local community. And indeed, here in Scotland, they've got a target of 2 gigawatts of energy capacity to be locally owned by 2030, which is quite a considerable amount. So it'll be easier to integrate renewable energy sources if we shift the grid down to this local level. That's really good, but the problem is it introduces this issue of who is going to try and match supply and demand. We've no longer got the national grid to do it for us. We're actually starting to put these decisions in the hands of the people who own the renewable energy sources, and hence in the hands of the community themselves, which means now the community is now facing these decisions that were previously faced by the national grid of how do we balance our supply and our consumption at any one point in time. And what my research is interested in is how can we use artificial intelligence and a multi-agent systems approach in particular to help communities do this. The image you can see down the right there, that Tower Power logo. So Tower Power is a scheme that's been trialled in high-rise blocks of flats in Edinburgh and Glasgow, where they put solar panels on the top of these flats, and then the energy that's generated by those solar panels is actually used by the people living in those flats themselves instead of being exported to the national grid. So that's exactly this kind of local community energy system that I'm talking about. Okay, so the key problem then is how can we flatten the demand curve? And we've heard a lot about flattening the curve recently with COVID-19, and it's actually exactly the same principle. So if you look at this figure here, what that dotted horizontal line would be for us is the maximum amount of energy that we're getting from our renewable energy sources on that day. And we want to make sure that the demand curve, the amount of the electricity that's being requested at any one point in time by the households in a community is not going above that line. So we're trying to flatten that curve, keep the demand curve lower than that dotted line, which is our energy capacity from renewable sources. If the curve goes above that line, that would then mean that the community would have to buy in some unclean energy from the national grid, which would cost them more money and of course would lead to more pollution. So we're trying to get that curve down below the dotted line so that as much as possible of the community's energy demands are met by these locally owned renewable energy sources. And that means we need to shift out the different times when different households are demanding their peak amount of energy. And that's the problem of load balancing. And we want to do this in a way that households and the families in those households will perceive as treating them fairly. So if we're going to try to get people to not all use all their appliances, things like electric heating, dishwashers, washing machines, and so on, at the same time, if we're going to try and get them to spread that out so we can flatten that curve, the only way we can really incentivize and motivate them to do that is if they feel that they're being treated fairly by that approach, that they're being treated fairly by the system. And fairness has two aspects or two dimensions to it. So one is the concept of distributive justice, which is how fair are the outcomes. So in our case, if we're going to have some mechanism that allocates to households, these are the times when you can run your various high-powered appliances, we want those outcomes, that distribution of times, to be perceived as fair by each household, so they're motivated to use this system, to buy into this system. But there's also an orthogonal dimension, which is that of procedural justice, where we think that people, and the psychological literature also suggests this, that people are not just interested in what the outcomes are, so in the times when they are able to run their high-powered appliances, people are also interested in, but is that procedure that's giving those outcomes, is that algorithm itself inherently fair, or is it advantaging some households at the expense of others? And this is the idea of procedural justice, procedural fairness, or algorithmic fairness. We want an AI mechanism to do this load balancing in a way that's fair from a distributional point of view, from an outcome point of view, but also fair from a procedural or an algorithm point of view, so people feel that the AI algorithm is treating them fairly, not advantaging some people at the expense of others, and they're satisfied with the outcomes of that process. And we think it's only if both of those are satisfied that people are going to buy into this system and actually use it. So what's the traditional solution for load balancing? The traditional solution for load balancing is to have prices set by the electricity company. And a classic way of doing this in the UK was with what's known as Economy 7 tariffs. So you can see an Economy 7 meter in the photo there. And with an Economy 7 tariff, you're offered a cheaper rate to use electricity at night. So the idea here is to flatten that curve by getting less people to use it at peak times, which is in the evening, and more people to do things at night when demand for electricity is less. So that will flatten the curve. And that's done by differential pricing, incentivizing people by offering them a cheaper rate to use the appliances at night. However, even though that is in operation, it's not been widely effective at regulating people's demand for electricity. It's not been widely effective at flattening the curve. And one reason for that is it inherently is discriminative against households with lower incomes. Households with higher incomes can just afford to pay the higher rate to use the appliances at the times that they'd like to. Households on lower incomes do not have that luxury. And so in that sense, I would say it's certainly not fair from a procedural point of view, from an algorithmic point of view, and also the outcomes are not fair either. And if we're going to do this locally at a community level, it would also be the question of, well, who's going to set the differential prices and how are they going to be set? And I think more fundamental, perhaps from a philosophical point of view, we should also be asking the question of, is a market-based pricing mechanism the best thing to be introducing into a community? Can we come up with an alternative to that that people might perceive as fairer? So we're working on coming up with an alternative to do that that's not based on pricing set by a centralized authority, but instead is based on a local and decentralized approach. And the idea is that households have a smart meter in their home that's really smart. So I hope there's nobody here that's from the energy companies, but current smart meters are not really smart because all they do is send data back to the energy company. We envisage a smart meter that's actually smart in terms of it can run software on it, and what it could run on it is a software agent. And the idea is then users would be able to, households would be able to input into their software agent or input into their smart meter the preferences for the times when they would like to run various high-powered appliances. The agent program running on their smart meter will then go away and negotiate with the agent programs running on the smart meters of other households in that community to come up with an actual schedule for when those appliances should be used. So we're looking at an agent-based negotiation mechanism. And our hypothesis is households will perceive this as fairer in comparison to a centralized pricing mechanism. So we've got two strands of work looking at this at the moment. One is doing some experimental work. So we're doing some experiments on Prolific, which is a system like Mechanical Turk, where we're going to get about 100 participants and we're going to get them to take part in a simulation. They will play the role of a household. They will undergo this load balancing process, either with the decentralized AI agent-based approach that we're suggesting, or with a centralized pricing mechanism. And then we're going to ask them some questions to ascertain which mechanism they perceive as treating them fairer. So that's one strand to our work. That's in collaboration with social psychologists. The other strand to our work is actually looking at this agent-based mechanism in simulation. So we can actually look at some of its properties and look at how efficient it is, whether it leads to outcomes that theoretically satisfy as many preferences of households as possible. So I'm going to briefly talk about today is that simulation and theoretical work. So in our simulation, agents, one agent represents one household, and they have different preferences for the times when they would like to use their various high-powered appliances. And each day in this simulation, each household or its agent will request 4 possible time slots when it wants to do things. Those time slots are each 1 hour, and so there's 24 in a day that are available. And a limited number of agents can be doing things in the same time slot, which corresponds to the peak energy generation capacity on that day from the solar panels. And we've now got 2 problems. We've got an optimization problem, which is we want to satisfy as many of the household preferences as possible, so they get the time slots that they actually want. But we've also got a social problem in that we want to do this in a way that households perceive as fair and that respects their privacy. And to address both the optimization and the social problem, we've developed a decentralized agent-based allocation mechanism for these time slots that ultimately could run on programmable smart meters. So we were inspired by some previous work that was done in the Petruzzi et al. 2013 paper. You can see the reference for that at the bottom there. And the idea of the mechanism in that paper is households are initially allocated their time slots at random. However, they can then propose to exchange, to swap time slots with other households to try to better satisfy their preferences. So I can propose to you, I'd like to swap my 6 AM time slot for your 4 PM time slot. You or your software agents can then decide, do I accept that exchange or not? And they considered 2 types of behavior that people, households, or their software agents might do in this scenario. One is that they might act in a purely selfish way, which is, if I'm selfish, I will only accept an exchange request from you if that's going to give me one of my 4 preferred time slots, and otherwise I will just reject it. But then they also considered a second type of behavior you might see in these systems, which is a more social type of behavior, where as well as agreeing to any exchange which benefits me, I will also agree to an exchange if I owe you a favor. So what do we mean by a favor? I owe you a favor if on a previous day you've given me one of the time slots that I wanted. So on a previous day, you've accepted an exchange request from me. So I'll always accept an exchange if it's in my immediate interest, if it's going to give me a time slot I want. But additionally, if I'm social, I will accept an exchange from you if I owe you a favor from a previous day. And this is the idea of introducing some computational formalization of social capital into the system, where the more favors you've given to other people, the more likely these are to be paid back in later days, and in later days will actually let you get the time slots that you want. So if we just do a bit of a run of that simulation, it looks like you can see on the graph there. So you can see the number of days on the x-axis. And on the y-axis, you can see the average satisfaction of the households, where the satisfaction of one household is the percentage of its time slot preferences that have been satisfied on that day. We can calculate in this system, because it's only a small system, so we're just looking at 96 households There's 24 hours in a day, and each hour can have 4 households using it at the same time. Because that's quite a small system, we can mathematically calculate what the optimal solution to that optimization problem would be, which is what you can see in the blue line there. And then what we see is if we run this exchange-based mechanism, we see that as the days go on, social individuals keep doing better and better until they actually get pretty close to the theoretical optimum allocation in terms of satisfying the largest number of their preferences, whereas the selfish households that you can see in that dotted purple line, as the days go on, they start doing worse and worse. This is because selfish individuals' households are not building up any social capital. They're not doing favours to other agents, which then means in turn on subsequent days, other agents will not do them any favours. They then pretty much start getting stuck with the allocations that they've got because nobody will exchange with them. Whereas the social individuals are doing really well because they're doing favours to each other. They're able to keep exchanging as the days go on and break out of a local optima in the solution. So that's good, but I think it raises a couple of unanswered research questions, which is actually to what extent do we really need this mechanism of tracking social capital, of tracking favours given and received? Is that necessary to incentivise agents, to incentivise households to act socially? And secondly, there was no form of learning in that scenario that I can see there. In a more realistic case, we would expect households or their software agents to learn to act in either a social or a selfish way based on which will be best for them, based on which will give them the best satisfaction. So those two questions have been left unanswered. We've had a go at answering both of them. So we redid the simulations and we introduced the possibility of turning the tracking of social capital, the tracking of favours given and received off in the model. And we can then ask the question, do social agents still do well even if you don't track social capital, if you don't introduce that into the mechanism? And secondly, we added the possibility of learning behaviours into the model. So an agent at the end of each day can go and look at how well the other agents have done. And if it sees the other agents have done better than itself, it will switch to their strategy. This lets us answer this question of whether purely self-interested agents just doing best for themselves will still learn to act socially, which is what we want, because if agents act socially, they do more exchanges and they ultimately satisfy more of their preferences. But somehow we've got to incentivize them to do this. So first of all, we looked at the effect of turning the tracking of social capital off in the mechanism. And what do we see here? Well, actually, we see if we turn social capital off, selfish agents still do badly and social agents still do well. So the numbers that you can see in these heat maps here are the average satisfaction of each household. So the average percentage of its time slot preferences that have been satisfied. On the y-axis, you can see the number of days that the simulation is being run for. And on the x-axis, you can see the maximum number of exchanges between households that are allowed on any one day. And what this graph basically is telling us is that we can turn social capital off in this mechanism, and it seems that selfish agents still do badly and social agents still do well. So that might suggest to us we don't need to go into all this palaver of tracking social capital. We could turn it off and we would do fine. However, the problem here is we're only considering a case where every agent in the system uses the same strategy. In general, that will not be the case. There's no reason for us to think every household's going to act the same way. And indeed, we don't want to force households to act in the same way. A big advantage of the decentralized agent-based approach is that we're not forcing every household to act in the same way. We're letting them enter their own preferences. And the idea is we would let a household tell its agent on its smart meter, you can either act more in a social way and accept a lot of exchange requests even if they don't benefit me, or you could act more in a selfish way and reject requests if they do not immediately benefit me. You as the household could specify that, and that information would be kept private to your agent and not shared with anybody else. So there's no reason to think in reality every household would either all be selfish or all be social. And so what we now need to consider is what if both types of agent are in the population. That's what we're considering on this slide here. We start each simulation out with 50% social households and 50% selfish households. And on the left, you can see the results if we do not track social capital, so we're not tracking favours given and received. And on the right, you can see the results if we do track social capital. So what does this tell us? If we start, I think, looking at the bottom row, because that's our big take-home message, if you're not tracking social capital, so that left-hand column, we see that in most cases, roughly half the agents end up acting socially and half the agents end up acting selfishly. And then if you look at the row above that, what we're seeing is when they're doing that, agents are less satisfied than they were before. They're less closer to reaching the theoretical optimum allocation of time slots to satisfy their preferences. So what this is telling us, this left-hand column, is if we don't have social capital in this mechanism, around half the agents will evolve or learn to act selfishly because that's what's benefiting them. And then in that case, the whole community is taking a hit because every household is less satisfied. On the right-hand side, though, we can see things are very different. So again, if we start at the bottom row, we can now see actually for quite a large range of parameters, all of the households have been incentivized to act socially. That's the 100s that we're seeing in those boxes there. And if we look at the row above that, we can see average satisfaction is higher. And we've done some statistical significance tests on comparing the left and the right, and we have confirmed that that difference indeed is statistically significant. And also, we think that the reason we're not seeing a massive absolute difference in satisfaction in terms of magnitude is because the problem we're working on is a small test case. If we had a harder problem, then we actually think you'd see much more of a difference between the case of satisfaction where individuals are social versus when they're selfish. So to wrap up then, what we've shown in our work here is that a time slot allocation mechanism that's based on social capital is able to flatten that curve. It can incentivize agents to reduce their peak electricity consumption. And moreover, it promotes social behavior in that system. It incentivizes even purely self-interested agents or purely self-interested households to act in a social way, to accept exchanges that are not immediately advantageous to them. That's good for the system as a whole, and it means overall more time slot preferences are satisfied, and overall then it's leading to good outcomes where the average satisfaction of households is high. And this suggests then that this could be a sufficient mechanism for demand side reduction for load balancing in a community energy system. It could actually synergize with a pricing model, because the time slots, the 4 time slots that you actually are allocated by this mechanism could be time slots when you were offered electricity at a cheaper rate. So that's another way that you could have a hybrid mechanism that integrates this with pricing. Our hypothesis is real humans will perceive this as treating them fairly, and we're just starting these psychological experiments now to see whether that's the case. So I think with that, I'll just thank a few people. So I'll thank Nathan Brooks, who's a PhD student at Keele University, who's done most of the simulation work for us, and my collaborator, James Borg, also at Keele, and much of this work has been funded by the Keele Institute of Liberal Arts and Sciences. So thank you very much, and if you've got any questions, we'll take them at the end.
Thank you very much, Simon. It's a very interesting talk. So now we have our Q&A session. So there are a number of ways that you can ask a question. You can ask it on the platform or the conference platform, or you can raise your hand in Zoom, or you can type a question in Zoom as well. So currently we don't have any questions, so maybe I can just start off the discussion. So there's a common theme between the 3 talks, and those were around data and privacy of data. So I was just wondering if I could ask our 3 speakers to maybe comment on their experience with lack of data and privacy, and what solutions I think there might be to this going forward so that we can leverage AI in this area.
Do you want me to start?
Sure, yeah,
I can do a very quick one about the privacy. One of the things we've just experienced that is quite interesting is it's the lack of understanding of what is the data, what is privacy, and you know, what an interesting thing we have right now is we have households that are allowing us to go in their flats and laser scan them in 3D. And then we say, can we take pictures? No, no, no. And well, when we laser scan it, we actually take a 3D detailed picture of your flat. And when we take a picture, we just take a 2D picture of your flat. But because they understand pictures, but they don't really understand laser scanning, the kind of thing, but they don't, like, somehow they were allowing us. And I think it's, so to some extent it's a pity, because maybe they make the wrong decision. Maybe they should allow either or both, or look at it differently. But I think in that case, the issue is the understanding, the communication about what their data is for a start, before even you start discussing how it will be used and how the privacy will be protected, etc. So I thought that was a really interesting case that we just experienced recently. If Francesco or Simon want to add something on their side.
Yeah, I think that's a common theme whenever we work with buildings, and especially the part of buildings that involves people in it. You know, so if I want to record information about what your home looks like and what the layout is, and that's very personal in a way. So I think it's inevitable that there's an issue there. I think it's, you know, as researchers, we need to make sure that the ethical consideration gets across very clearly and very fairly. You know, even if our data is constantly used in other cases without us maybe knowing it, but you know, I don't think we need to go down that route as researchers.
Yeah, and it's similar issues that we've got. So at the moment, we've mainly been basing it on synthetic data or on average consumption data, whereas really we would actually like to get data on actual times when real households are using their various appliances. We're actually hopefully getting some data from Portugal. So there has been a study there where they have got smart meters in people's homes that actually track it down to the usage times of the individual appliances. And they are happy for us to use that data. So that'll help us make our models more realistic. But yes, in general, it's a challenge. And I think the other issue with privacy is we think that's actually one of the advantages of the decentralized approach that we're working on, is it means that your time slot preferences do not have to explicitly be shared with a centralized authority, which we think is a real advantage of a decentralized agent-based approach, is keeping that data locally on the local households agent.
It's interesting, that question of data sharing. Do you feel that that might be more of an option going forward, either through the energy companies or from different countries?
I mean, yeah, I mean, so I mean, I think in general there's been some resistance to smart meters, at least in the UK, and one of the reasons for that is this idea of people don't necessarily want their consumption data being fed back even just to the energy company. They're not too keen on that. So I think there is some resistance to it.
I wonder also, I mean, typically there's also the novelty effect, that, you know, you ask them to change, but if they were to move a flat that already has all these things set up, etc., they just would think it's normal. And, you know, and at some point we will probably all think it's normal, because that will become standard thing. So there is also the aspect of transitioning from a state of comfort and understanding into another state where you will eventually become comfortable as well. Yeah.
I'm just going to pause for a minute, see if anybody wants to raise their hand or ask a question from the delegates. I have lots of questions.
Yeah, I can ask
okay.
as well.
All right, so I've got another question then. So if we adopt artificial intelligence, there's obviously recently been a lot of attention on explainable AI. So how transparent do these methods have to be, and transparent for whom? For the end user or for the developers, this type of thing?
I don't know. If I start, I would say it all depends on the context, I think, to some extent. The way we use AI right now in our project, I don't think there is any clear issue of explainability, but you know, I would know some contexts where, well, if I know of a context, for example, in civil engineering. So the new Forth Bridge crossing in South Coast Ferry is actually equipped with a lot of sensors. And these sensors actually, these are developing AI-based techniques to monitor the structure and possibly make calls on when to close the bridge if necessary for whatever reason. Now, if the call is made one day and the bridge has to be closed, then the media will come and say, why did you close it? Because the AI told us. And so that in those cases, it's going to be, and that's just closing the bridge, but the decisions could have been made, you know, why did the bridge collapse? And the AI said it was fine. So there are cases which are much more serious in terms of the impact on people than in the current project we're on. I don't think we are facing that, but I'm sure there are some other contexts where it becomes, explainability becomes seriously important.
That's a good point. Good point about the audit trail as well, something goes wrong. And what about from a social science perspective, Simon, your end users, do they need explanations if they're given a time slot, they don't quite understand why?
Yeah, so we think so. We think that's actually one of the advantages of the mechanism that we're looking at, is it is relatively simple to give an explanation to people of why they've got a particular time slot. And in particular, the idea of social capital, we think, is inherently intuitive to people. It's kind of something we implicitly use in our daily lives and interactions with others. We kind of do know, you know, oh yes, this person generally is a helpful person, they do favors, and that person's not. And so I think being able to give an explanation along the lines of, look, you've not got the time slot you wanted today, but that means that you will get it tomorrow. So you've kind of done a favor to somebody today, and then that will be repaid by somebody else tomorrow. I think that is quite an intuitive explanatory concept.
And how you present that, either in natural language explanation or some kind of visual, is also interesting. Great. Any other questions? I was going to ask about your experience with working with industry. Do they see the benefits of AI, or do you think we need to educate industry more on the potential of that AI can bring to their business?
I think they do, surely. The construction industry is starting very quickly to realize the huge potential. There's even like engineering companies who are investing in R&D internally, funding AI-based projects. You know, there's a company in London, they're trying to do the sort of, instead of scan to bin, but hand drawing to bin. So they're trying to map engineers just sketching the structure on the paper and trying to see if that can be instantly transferred into this software tools for building design. So I think they can see the cost benefit, but also the time benefit. You know, the two are related, obviously, but that means a lot in long-lasting projects such as buildings and infrastructure.
Yeah, I agree. I think they totally see. I think there's they may have high expectations sometimes in terms of, oh, that's going to solve our problem. But they do, and in fact, I think a lot of companies have extremely valuable data to develop AI-based systems that they don't necessarily realize they do. But like, so I'm about to start a project, for example. Well, we hope actually to start a project where with a company that turns out that they have tens of thousands of labeled pictures of defects inside buildings. Now they know what they want to do with it, but it took them quite a while to realize that they were sitting on the mine of data that was extremely useful to develop the type of application they were looking at. Now, you know, when you talk to them, they expect, you know, 100% accuracy, 100% this. That's the thing that, you know, need to, obviously we will have lots of data, so we're lucky, but this all managing the expectations of what you can achieve, I think, is important. But I think, yeah, there's a great understanding of the value, and I think especially in sustainability, because people realize it's very complex problems. It involves lots of domains, as I said, a lot of areas that as humans, it just struggle to making sense of a lot of things, and having new computers helping us out, I think people quite realize it's valuable, or it's worth investigating.
Sure.
Yeah.
Well, that's very encouraging to hear. Great. And does anybody have any final comments or questions from the delegates? It's been quite quiet today.
They're quiet. There's still attendance.
Yeah.
No,
So
you asked. I don't know. I had some question
Yeah.
to Simon actually, but I guess you started answering that, and you've done some psychological analysis. It's just, do we think people would be willing spending time figuring out their preferences, or is that something that you know, people just don't want to be bothered with these kind of things? They just expect that this balancing will be done for them and it will be fair. I think it's quite interesting. The whole project I think is good, but the whole human aspect I think is quite interesting in those. Like, will I be, you know, how often would they have to change their requirement, or is it something that would just need to do the day they move in, or is that something that would need to be
yeah, so what, yeah, no, that's an excellent question. So what we really want to do is to try and make this as easy and as automated as possible for people. So certainly in terms of the exchanges and whether they're accepted or not, that would automatically be done by the agent program that's running on their smart meter. So in terms of the preferences, that would depend how often they might change. I would think those might be pretty static in terms of these are the preferences for when I'd like to do washing or dishwasher or this kind of thing. I guess that would be relatively static, and you could program that in, well, this is my preferences for weekdays, this is my preferences for weekends, and that I think would be fairly static. Yeah. So that's not something I would envisage them having to do each day, no.
The other question I had about this is, one of the major big high-powered appliance that is coming in the house is the car. Now, how overwhelming the car is in terms of energy demand compared to the rest of the house, and in that case, because we will have to increase the supply for covering that, essentially it will just be about timing when to charge the car, because that's going to be the big one in terms of energy demand, I suspect, but I don't actually know.
Yes, so cars are an interesting one, and of course also the possibility to use them effectively as battery storage also, yes, which is nice. So that also helps add a bit more flexibility into the system. But I guess you are right that given that probably would be the highest demand, that might be something that's relatively harder to shift. I mean, I suppose there could be some possibilities of shifting charging times, yeah, depending on how long it takes to charge. So there's a possibility certainly for doing it in different time windows at night.
Yeah.
So yeah, I think that will introduce new challenges, but also some new kinds of opportunities with the possibility of using them as short-term battery storage, which adds a bit more flexibility.
Yeah, that's really cool. Thanks.
Thank you very much. I'm getting pinged that we're coming to the end of the session. So I just want to take this time to thank our speakers, Fred, Francesco and Simon. And I'd like to thank our delegates for attending. And next on the agenda is lunch. I'm afraid you have to go and find your own lunch in this kind of conference. But I just want to say thanks very much. And it's been a very, very interesting session. It's been very enlightening and made us all think about where we're going in terms of sustainability and AI. So we'll end here, and thank you very, very much. Take care.
Yeah.
Thank you very much. Thanks, everybody. Bye-bye.